A comparison sort is a type of sorting algorithm that only reads the list elements through a single abstract comparison operation that determines which of two elements should occur first in the final sorted list. The only requirement is that the operator obey two of the properties of a total order: if A per mole currency B and B A per mole currency C, then A per mole currency C, for all A and B either A per mole currency B or B A per mole currency A. It is possible that both A per mole currency B and B A per mole currency A. In this case either may come first in the sorted list. In a stable sort, the input order determines the sorted order in this case. A metaphor for thinking about comparison sorts is that someone has a set of unlabeled weights and a balance scale. Their goal is to line up the weights in order by their weight without any information except that obtained by placing two weights on the scale and seeing which one is heavier. Examples. Some of the most well-known comparison sorts include quicksort, heap sort, merge sort, intro sort, insertion sort, selection sort, bubble sort, odd-even sort, cocktail sort, cycle sort, merge insertion sort, smooth sort, TOM sort. Performance limits and advantages of different sorting techniques. There are fundamental limits on the performance of comparison sorts. A comparison sort must have an average case lower bound of I copyright, and log n, comparison operations, which is known as linear arithmetic time. This is a consequence of the limited information available through comparisons alone or, to put it differently, of the vague algebraic structure of totally ordered sets. In this sense, merge sort, heap sort, and intro sort are asymptotically optimal in terms of the number of comparisons they must perform, although this metric neglects other operations. The three non-comparison sorts above achieve O(n) performance by using operations other than comparisons, allowing them to sidestep this lower bound. Note that comparison sorts may run faster on some lists. Many adaptive sorts such as insertion sort run in O(n) time on an already sorted or nearly sorted list. The I copyright and log n lower bound applies only to the case in which the input list can be in any possible order. Also note that real-world measures of sorting speed may need to take into account the ability of some algorithms to optimally use relatively fast cached computer memory, or the application may benefit from sorting methods where sorted data begins to appear to the user quickly as opposed to sorting methods where no outputs is available for display until the whole list is sorted. Despite these limitations, comparison sorts offer the notable practical advantage that control over the comparison function allows sorting of many different data types and fine control over how the list is sorted. For example, reversing the result of the comparison function allows the list to be sorted in reverse. And one can sort a list of tuples in lexicographic order by just creating a comparison function that compares each part in sequence. Function tuple compare lefter, leftb. LEFTC, if lefter per mole righter, return compare, lefter, righter, else if LEFTB a per mole RIGHTB, return compare, LEFTB, RIGHTB, else, return compare, LEFTC, RIGHTC. Balanced ternary notation allows comparisons to be made in one step, whose result will be one of less than, greater than, or equal to. Comparison sorts generally adapt more easily to complex orders such as the order of floating point numbers. Additionally, once a comparison function is written, any comparison sort can be used without modification. Non-comparison sorts typically require specialized versions for each data type. This flexibility, together with the efficiency of the above comparison sorting algorithms on modern computers, has led to widespread preference for comparison sorts in most practical work. Alternatives: some sorting problems admit a strictly faster solution than the I copyright and log n bound for comparison sorting. An example is integer sorting, where all keys are integral. When the keys form a small range, counting sort is an example algorithm that runs in linear time. Other integer sorting algorithms, such as radix sort, are not asymptotically faster than comparison sorting, but can be faster in practice. The problem of sorting pairs of numbers by their sum is not subject to the I copyright, now squared log n, bound either, The best-known algorithm still takes O, now squared log n, time, but only O, now squared comparisons. Number of comparisons required to sort a list. The number of comparisons that a comparison sort algorithm requires increases at least in proportion to, where is the number of elements to sort. This bound is asymptotically tight. Given a list of distinct numbers, there are n factorial permutations, exactly one of which is the list in sorted order. The sort algorithm must gain enough information from the comparisons to identify the correct permutation. If the algorithm always completes after at most n steps, it cannot distinguish more than 2 cases because the keys are distinct and each comparison has only 2 possible outcomes. Therefore, or equivalently, from Stirling's approximation we know that is. This provides the lower bound part of the claim. An identical upper bound follows from the existence of the algorithms that attain this bound in the worst case. The above argument provides an absolute, rather than only asymptotic lower bound on the number of comparisons, namely comparisons. This lower bound is fairly good, but it is known to be inexact. For example, but the minimal number of comparisons to sort 13 elements has been proved to be 34. Determining the exact number of comparisons needed to sort a given number of entries is a computationally hard problem even for small n, and no simple formula for the solution is known. For some of the few concrete values that have been computed, see a 036604. Lower bound for the average number of comparisons, a similar bound applies to the average number of comparisons. Assuming that all keys are distinct, that is every comparison will give either A, B or A, B, and the inputs is a random permutation, chosen uniformly from the set of all possible permutations of n elements, it is impossible to determine which order the inputs is in with fewer than log 2, n. Comparisons on average. This can be most easily seen using concepts from information theory. The Shannon entropy of such a random permutation is log 2, n bits. Since a comparison can give only 2 results, the maximum amount of information it provides is 1 bit. Therefore after k comparisons the remaining entropy of the permutation, given the results of those comparisons, is at least log 2, n AAK bits on average. To perform the sort, complete information is needed, so the remaining entropy must be 0. It follows that k must be at least log 2, n. Note that this differs from the worst case argument given above, in that it does not allow rounding up to the nearest integer. For example, for n equals a3, the lower bound for the worst case is 3, the lower bound for the average case is shown above as approximately 2.58, while the highest lower bound for the average case is 8/3, approximately 2.67. In the case that multiple items may have the same key, there is no obvious statistical interpretation for the term average case, so an argument like the above cannot be applied without making specific assumptions about the distribution of keys. Notes: http planetmath.org lower bound for sort in GHTML, Pachzarsky, Marcin. Towards optimal sorting of 16 elements Marcin Pachzarsky, the Ford-Johnson algorithm is still unbeaten for less than 47 elements. Inf. Process. Let 101, 3, 126 to 128 doi, 10.1016/jpl. 2006.09.001, References, Donald Knuth. The Art of Computer Programming, Volume 3, Sorting and Searching, 2nd edition. Addison Wesley, 1997. ISBN 0-201-89685-0. Section 5.3.1, Minimum Comparison Sorting, PPA 180 €197. Thomas H. Corman, Charles E. Lesserson, Ronald L. Revest, and Clifford Stein. Introduction to Algorithms, 2nd edition. MIT Press and McGraw-Hill, 2001. ISBN 0-262-03293-7. Section 8.1 Lower Bounds for Sorting, PPA 165 €168.